There is a growing need to understand how climate change could affect ecosystems and economic production capacity in natural resources intensive systems, such as agriculture and forestry. The productivity of the global land use sector is susceptible to changes in average temperature and regional precipitation patterns, which will be especially challenging as they continue to face rising global demands for food, fiber, energy, and natural climate solutions. Continued efforts to understand how climate change will interact with socio-economic and environmental demands for land resources can inform mitigation and land use policy design and adaptation planning. There is substantial literature devoted to agricultural sector climate impact assessment using different methods, including bottom-up empirical technicals or top-down integrated systems modeling. Recent multimodal assessment developed by Agricultural Model Intercomparison Project have contributed significantly to this domain, and more recent efforts are linking agricultural climate impact scenarios with mitigation policy assessments. However, considerably less attention has been devoted to quantifying potential future climate impacts in forestry. Forests have an outsized influence on terrestrial carbon storage levels and local climate systems relative to economic contribution of the sector. The net effect of changing climate conditions on the forest sector include both market implications, such as how changes in productivity affect harvest levels and forest product markets, and forest management implications, such as how management changes to adapt to climate change affect ecosystems and climate services such as forest carbon sequestrations. Given the heterogeneity in forest management technicals and biological growth rate for different tree species, assessing potential impacts from climate change decades in the future requires a dynamic approach that links management decisions under different productivity change scenarios to socioeconomic systems. That is, quantifying the impacts of climate change on the forest sector should include accounting for exogenous climate-driven productivity changes for different forest types as well as endogenous adaptation responses to changing productivity regimes. Further, impact assessment should evaluate how climate-induced changes in forest productivity and regional adaptation responses could also shift forest inventories, carbon sequestration rates. Adaptation responses can limit economic damages to the sector by maintaining production and consumption levels over time for scenarios that adversely affect forest productivity. However, without complementary policies to protect inventories or carbon stocks, such scenarios could result in lower carbon sequestration rates. Reduced sequestration would then reinforce negative climate feedback effects, similar to those associated with growing forest fire risks. This is a summary of one of our recent publications titled Projecting U.S. Forest Management, Market, and Carbon Sequestration Responses to a High-Impact Climate Scenario. This study builds on previous literature evaluating potential climate change impacts in the U.S. forest sector. We developed structural dynamic simulations of climate scenarios using forestry components of the forest and agricultural sector optimization model with greenhouse gases, FASOM, GHG, developed by Adams and his team in 1996, coupled with a forest growth model based on empirical relationships for individual tree species, to show how anticipated changes in forest productivity affect management and harvest dynamics in key domestic timber-producing regions. We compare market, management, and carbon sequestration projections across scenarios and then quantify estimated net economic impact of climate change. We discuss potential adaptation responses to climate change in the U.S. forestry sector, which could include shifting the spatiotemporal distribution of harvest, changing forest types, increasing management intensity, and expanding or contracting regional mill capacity. Our analysis makes several contributions to the literature. First, we linked empirically derived tree species-specific growth and survival equations to estimate how climate inputs, such as mean annual temperature and total annual precipitation, affect plot-level species composition and yields. This approach deviates from economic modeling literature on forest climate impacts, as most studies use process model projections to adjust productivity of forest ecosystems over time. Instead, we apply our empirical technique to adjust the growth and yield tables for different forest types included in FASOM GHG, that is our model. Second, we simulate long-term economic and forest ecosystem impact of extreme climate changes. We apply the yield-adjusted FASOM GHG dynamic optimization model of the U.S. forest sector under a climate change scenario, representative concentration pathway, RCP 8.5, represented by 6 different climate circulation model, GCM projection. Although all GCM outputs used in this analysis link to the RCP 8.5 scenario, for the purposes of this study, we refer to each GCM model run as a separate climate scenario. The modeling framework allows us to project potential management and market implications of alternative climate futures using a dynamic framework. We run intertemporal dynamic simulations to project the spatiotemporal distribution of harvest patterns and inventory changes for alternative expected climate and socio-economic futures. This approach allows us to assess adaptation responses to changing temperature and precipitation input, assuming full information via the intertemporal function of the model on future growth and yield dynamics under climate change. Third, our analytical approach recognizes that manufacturing capacity in the forest product sector is not fixed over time. Mill capacity can contract or expand within a region depending on the relative cost advantages and standing forest inventories at or near harvest age. Under climate change, regional mill capacity could migrate as an adaptation mechanism, reflecting how climate-driven changes in forest productivity and inventory could affect the flow of capital investment in the sector. Previous U.S. forest sector climate impact assessments have not incorporated the potential role of mill capacity expansion or contraction as an adaptation response. Finally, similar to other previous studies carried out by Anderson and team in 2020 and Tihen and team in 2016, we find that U.S. forest markets are fairly resilient to high warming scenarios, at least through the end of the century, though longer-term impact could be more substantial. That is, net economic welfare changes, measured as the sum of simulated consumer and producer surplus changes, are less than 1% across all climate scenarios. However, our results also show that regional inventory changes, mill capacity utilization, and carbon sequestration could vary dramatically across scenarios. These results suggest that while forest market may be fairly resilient to climate change in aggregate, losses in carbon sequestration capacity and forest inventories may require complementary policies to address these impacts. We find negative impact on the sector under most scenarios, maxing out at approximately $2.6 billion per year in damages. However, near-term damages from reduced carbon sequestration capacity, estimated using the social cost of carbon, are more than double consumer and producer losses across many of our model scenarios. I am Olakunle Sodiya, a Southeast Climate Adaptation Science Center 2021-22 Global Change Fellow. I am a PhD student in the Department of Forestry and Environmental Resources in the College of Natural Resources at NC State University. This research was led by Dr. Justin Baker and his team of researchers, including myself.